When someone cuts neutral and ground wires in a three-phase power system, several factors can contribute to a fatal electrocution. The primary issue is that the person's body becomes a pathway for current to flow from the energized phase wires to the ground. Cutting the neutral and ground wires disrupts the designed current flow path, which normally allows current to return to the source. The possibility of electrocution arises from a combination of electrical phenomena. Firstly, induction. When the neutral wires are cut, a voltage can be induced in the remaining energized phase wires. This occurs due to the magnetic field created by the current flowing through those wires. Secondly, capacitance. The energized phase wires form capacitances with the ground and the building structure. This capacitance provides an alternative path for current to flow, potentially through a person's body. Thirdly, a high resistance ground. Severing the ground wires increases the resistance of the ground path. Consequently, current seeks the path of least resistance, which can unfortunately be through a person who is in contact with the system. Fourthly, the high voltage of the 415-volt system significantly increases the danger. Even with a reduced resistance path through a person's body, the high voltage can drive a lethal amount of current. The sequence of events leading to electrocution typically unfolds as follows. Firstly, the person cuts the neutral and ground wires, disrupting the normal current flow. Secondly, induction and capacitance effects generate a voltage on the energized phase wires. Thirdly, the person's body becomes the path of least resistance for current to flow from the energized wires to the ground. Fourthly, a high voltage and resulting high current cause electrocution. Several additional factors can exacerbate the risk. A wet or conductive environment can further reduce the resistance of the ground path, increasing the current flow through the body. Direct contact with exposed energized wires provides an immediate and low resistance path for current. The absence of personal protective equipment such as insulated gloves or rubber boots removes crucial barriers against electrical shock. To understand these dangers more deeply, let's consider each factor in detail. Induction, in this context, refers to the generation of a voltage in a conductor due to a changing magnetic field. When alternating current flows through a wire, it creates a magnetic field around that wire. If another wire is placed within this magnetic field, a voltage can be induced in that second wire. The magnitude of the induced voltage depends on several factors, including the strength of the magnetic field, the distance between the wires, and the orientation of the wires relative to each other. In a three-phase system, the currents in the three-phase wires are constantly changing, creating complex and dynamic magnetic fields. When the neutral wire is cut, the return path for these currents is disrupted, which can alter the magnetic fields and increase the induced voltages in the remaining energized phase wires. Capacitance, the ability of a system to store electrical charge, also plays a significant role. In this scenario, the energized phase wires, the ground, and the building structure form capacitors. A capacitor consists of two conductive plates separated by an insulating material. In this case, the energized wire and the ground act as the conductive plates, and the air or other insulating materials between them act as the insulator. When a voltage is applied across a capacitor, it stores electrical charge. The amount of charge stored depends on the capacitance value and the applied voltage. Alternating current can flow through a capacitor because the capacitor is constantly charging and discharging. The higher the frequency of the alternating current, the easier it flows through the capacitor. In the case of cut neutral and ground wires, the capacitance between the energized wires and the ground provides a path for current to flow, even when the normal return path is interrupted. This current can flow through a person's body if they come into contact with both an energized wire and the ground. A high resistance ground condition is created when the ground wires are cut. Ground wires are designed to provide a low resistance path for fault currents to return to the source. This low resistance path ensures that when a fault occurs, such as a short circuit, a large current will flow, tripping a circuit breaker or fuse and quickly de-energizing the circuit. When the ground wires are cut, the resistance of the ground path increases significantly. This means that when a fault occurs, less current will flow through the ground path, and the circuit breaker or fuse may not trip. As a result, the fault current may find an alternative path to ground, such as through a person's body. The higher the resistance of the ground path, the more current will flow through the alternative path. The high voltage of a 415-volt system exacerbates the risks associated with induction, capacitance, and high resistance grounds. Voltage is the electrical potential difference that drives current through a circuit. The higher the voltage, the more current will flow through a given resistance. In the case of electrocution, the resistance is the resistance of the person's body. A typical human body has a resistance of between 1000 ohms and 100,000 ohms, depending on factors such as skin dryness and the path of current flow. At 415 volts, even a relatively high body resistance can allow a lethal amount of current to flow. For example, if a person has a body resistance of 10,000 ohms, the current flow would be approximately 0.415 amps, which is enough to cause serious injury or death. Furthermore, the sequence of events leading to electrocution must be carefully considered. Cutting the neutral and ground wires is the initiating event that disrupts the normal current flow paths. This disruption sets the stage for induction and capacitance effects to generate voltages on the energized phase wires. When a person then comes into contact with both an energized wire and the ground, their body becomes the path of least resistance for current flow. The high voltage and resulting high current then cause electrocution. Additional factors, such as a wet environment or the absence of personal protective equipment, can significantly increase the risk of electrocution. Water is a good conductor of electricity, so a wet environment reduces the resistance of the ground path and increases the current flow through the body. Personal protective equipment, such as insulated gloves and rubber boots, provides an additional layer of protection against electric shock. Insulated gloves prevent current from flowing through the hands, while rubber boots insulate the body from the ground. To prevent electrocution in these types of situations, several safety measures should be implemented. Firstly, always de-energize the circuit before working on it. This means turning off the circuit breaker or fuse that supplies power to the circuit. Use a voltage tester to verify that the circuit is de-energized before touching any wires. Secondly, use proper lockout/tagout procedures to prevent the circuit from being accidentally re-energized while you are working on it. This involves placing a lock and tag on the circuit breaker or fuse to indicate that it is being worked on. Thirdly, wear appropriate personal protective equipment, such as insulated gloves and rubber boots. Fourthly, never work in a wet environment. If the environment is wet, dry it thoroughly before working on the circuit. Fifthly, inspect all tools and equipment before use to ensure that they are in good working condition. Replace any damaged or worn tools. Sixthly, be aware of the potential hazards of induction and capacitance. When working on energized circuits, use appropriate grounding techniques to minimize the risk of induced voltages. Seventhly, if you are not qualified to work on electrical circuits, do not attempt to do so. Call a qualified electrician. Understanding electrical safety concepts is critical in preventing accidents. Electrocution can occur when a person becomes part of an electrical circuit, allowing current to flow through their body. The severity of the shock depends on several factors, including the amount of current, the path of the current through the body, and the duration of the shock. Even a small amount of current can be fatal. For example, a current of only 0.1 amps can cause muscle contractions, making it difficult to let go of the energized object. A current of 0.1 amps can cause ventricular fibrillation, a condition in which the heart beats erratically and cannot pump blood effectively. A current of 1 amp can cause cardiac arrest and death. The path of current through the body also affects the severity of the shock. Current that passes through the heart or brain is more likely to be fatal than current that passes through other parts of the body. The duration of the shock also affects the severity of the injury. The longer the shock lasts, the more damage it can cause. There are several ways to protect yourself from electric shock. Firstly, avoid contact with energized electrical circuits. Always assume that a circuit is energized until you have verified that it is de-energized. Secondly, use insulated tools and equipment. Insulated tools and equipment prevent current from flowing through your body if you accidentally come into contact with an energized circuit. Thirdly, wear appropriate personal protective equipment, such as insulated gloves and rubber boots. Fourthly, never work in a wet environment. Fifthly, be aware of the potential hazards of static electricity. Static electricity can build up on your body and discharge when you touch a grounded object. This discharge can cause a painful shock. To prevent static electricity buildup, wear clothing made of natural fibers and avoid working in dry environments. Sixthly, follow all electrical safety procedures. Electrical safety procedures are designed to protect workers from electric shock. Follow these procedures carefully to prevent accidents. In summary, cutting neutral and ground wires in a three-phase power system creates a dangerous situation due to the disruption of normal current flow, induction, capacitance, high resistance ground, and the presence of high voltage. Awareness of these factors and adherence to safety procedures are essential to prevent electrocution.